Hi, this is Tim Weber from South Texas College coming to you with a video on sensation. And so today we'll look at various aspects of that topic. Let's go ahead and bring up the outline that we'll be using on the screen. You'll notice it's actually part of a chapter on sensation and perception. And so let's get started here. I'll get myself off the screen and get a pointer here so that I can show you where I am. Okay, here we go. All right. So let's first have a look at what is sensation, what is transduction, and what is perception. Sensation is the ability to detect various types of stimuli in our environment, stimulus energies such as light particles, sound waves, pressure, heat and cold, so types of stimulus energy being detected. Now that's simple raw information. Sensation in and of itself does not tell us what is the source of those stimulus energies or what they mean. It's just raw information. Transduction is the process by which our sensory receptors, those cells that pick up those stimulus energies, are able to transform those stimulus energies into information that our nervous system can deal with. So maybe if you've done any audio recording, you might have heard of a microphone also called a transducer. Well, those microphones transduce, in other words, they take sound waves and they turn them into electrical signals that your audio equipment can deal with. Well, transduction in humans is then turning it that that stimulus energy from our environment into a signal that our nervous system can deal with, turning it into neural impulses that can travel through our neurons and be then transmitted to our brain. So the third step of this process would be perception, and that would be where our nervous system begins to interpret those sensory signals that are coming in and sorting through them, determine what they are and what they mean to us. So that's the entire process. We'll be focusing today on sensation. So one of the first things that scientists began studying regarding sensation was what they called the absolute threshold for sensation. This is the weakest stimulus level that we can reliably detect for a particular sensory system. So, for example, they found for light, the light of a candle flame 20 miles away on a perfectly dark and clear night was a typical human capability. Now, you might not believe it because those conditions are very rare to have a perfectly clear and dark night. But if you were to experience those conditions, the average person can detect that. Amazing, right? When it comes to sound, they found the sound of a watch ticking across the room, quiet room. That one might sound a little bit more reasonable. Maybe you've experienced that, although now we don't have ticking watches much anymore. Pressure, this one's kind of funny. They express this as the average person can detect the pressure of a bee's wing falling on their cheek from 1 centimeter away. That's the average capability. But that kind of makes sense. You know, sometimes you'll feel a mosquito land on your arm or something like that. It's kind of similar. With taste, the ability to taste that there is something in the water. If we add a teaspoon of sugar to a couple gallons of water, or odor, a drop of perfume in a 1 or 2 bedroom apartment is a typical capability of humans. So absolute threshold, what we typically can detect reliably. And by the way, they gauge reliably as 50% or more of the time, okay? Now, that might make you wonder, if you're looking at this diagram, well, there are stimuli that exist that don't reach those levels, what they call subliminal stimuli. And the question might come to mind is, well, do we maybe detect these somewhat? Are we maybe detecting them and are not aware of them, and so on? So psychologists also set out to study this subliminal stimuli and conducted experiments then to find out, do we detect things below that threshold? And if so, can these subliminal stimuli have any effect on us? So in order to study this, many experiments were conducted. And let me go ahead and give you a little bit of a window into how that's done and the results of these. So let me see, I want to bring up our whiteboard here. Okay, all right. So in these experiments, generally they would start out with a priming stimulus. And in many of these, there would be either a pleasant scene. We'll just put a smiley face here for the pleasant priming stimulus, or there would be an unpleasant one. Okay. Yeah, maybe for the pleasant one, there would be a couple holding hands on the beach at a nice sunset or something. Or maybe the unpleasant one, what, dead body or something like that. Okay. So, that's out of focus. Let's fix that. That's good as it gets. Yeah. There we go. Oh, no. Yeah, that's what happens when you try to fix things, right? Oh, let me see. Okay, I think we're back on. All right. So the priming stimulus only visible for a few milliseconds, not long enough that the subject knew that anything was on the screen, subliminal. That was then followed immediately with what they call a masking stimulus. And something was projected on the screen to sort of wash away, if you will, in the after image of that. It might be just kind of one of those starry night kind of scenes, or sort of static looking, if you will. That then was followed by target stimulus. So in many cases, the target stimulus was simply a person, and the subject then was to rate that person on some quality, desirable quality, like likableness or trustworthiness, things of that nature. Okay, so did it make a difference whether they saw the pleasant or unpleasant scene subliminally before seeing the target stimulus? Did they rate the target stimulus differently based on that subliminal stimulus seen previously? The answer to the question is yes. They consistently enough rated it higher if they had seen the pleasant scene, or lower if they had seen the unpleasant scene, that we can say the priming stimulus, subliminal priming stimulus, did have an effect on their ratings. It was statistically significant. Now, here's where something important comes in: effect size. So, how much did the subliminal priming stimulus affect their ratings? Only a little. So, in fact, even though this consistently had an effect, it was a rather weak effect. They also found that the effects of the subliminal stimulus wore off very quickly. And so that if much time passed before they did the rating, the effect evaporated very rapidly. And this also required very specific conditions here. A subliminal stimulus that was long enough to have an effect, yet short enough to not be noticed. And also, again, the timing between each of these stages had to be just right or nothing happened. So we can say, yes, subliminal stimuli under very precise conditions may have an effect, although that effect is very brief and it is very, very small. Okay. In fact, when compared to priming with stimulus that is supraliminal, in other words, that can be consciously perceived, the consciously perceived priming stimulus was much more powerful in affecting the ratings than the subliminal stimulus. So things that we can consciously be aware of tend to have a much stronger influence on us than things that we are not consciously aware of. Okay, so let's go back to here. Oh, yeah, okay. So the next thing that we might want to look at is, well, if these subliminal stimuli do have some effect, or can they be used to influence people? And so one of the things that psychologists picked up in order to study this was the use of subliminal persuasion recordings. And maybe you've run across these. You can go on the internet and find lots of them on YouTube and stuff like that. And so they will say that within this recording, they have embedded subliminal suggestions that are designed to help you with something or another. And so the question would be, well, are these recordings really effective? Do they do anything? And if they are effective, well, why are they effective? So to study this, psychologists came up with a really clever type of study. And again, numerous of these have been done. It's not just one, so it's been replicated in numerous different ways. And what they did is they presented subjects with one of two recordings. Okay. Now, this was done back in the days when they had cassette tapes. Anybody knows what those are? Or CDs. Maybe some of you still know what those are. Okay. And okay. So one group was given a recording. Let's say it's on a CD, okay? And this was labeled as having suggestions for better sleep. And the subliminal messages were consistent with that. They also were actually for improved sleep as well. Okay. Group 2 was given CDs with recordings, also labeled, labeled improved, I just put an arrow for improved, self-confidence. However, the messages on their CD were for better sleep. So they were not consistent. Okay. Their label said improve self-confident. The messages were for better sleep, just like the first group. So they then had the participants use the recordings for a couple weeks and then came back and asked them whether they had any effect. So did the participants find that there was any effect? Well, what about group 1? You suppose they said that it had an effect? they consistently said yes, it seemed to work. And when asked, well, what effect did you experience? What do you suppose they said? You're going to say, well, of course, must be better sleep, because that's what it said, and that's what the subliminal messages were for. Okay, well, that all makes sense. What about group two? What do you suppose happened here? Did they say that the recording had an effect on them? Yes, they also consistently said that it did have an effect. Now, here's where it gets interesting. So, what effect did group two say that the recording had? Well, if you guessed better sleep, you're correct. Notice, whoops, here we go. See, if I'm not thinking, even I can make a mistake, right? I'm trying to think of two things at once. Yes. Yeah, they actually said, if you said better sleep, you were wrong. They said it improved their self-confidence. Okay, well, why would they say that? Well, the label that they saw on the CD said it was for self-confidence. They couldn't hear the subliminal message, so they went with what they saw. That's what it produced. Okay. Now, some of you are looking at this and you're saying, hey, you know what? This sort of suggests that maybe these subliminal recordings work primarily by placebo, and that the label produces an expectation, which is then produced regardless of what the subliminal messages might be. And so it appears that the primary method that these work by are by placebo rather than the actual effects of the subliminal message. Now, we're not saying that I'm not saying that the subliminal message would have no effect. It may have some small effect, but again, the effect would have been tiny as compared to the expected effect based on the label, which was consciously perceived. So again, the conscious stimulus seems to be the more powerful once again. Okay, so let's go back to our outline here. So one of the other phenomenon that were studied is the difference threshold. So what is the smallest difference between two stimuli that can be reliably detected? So we're comparing two stimuli. Is one different than the other? The smallest difference then can be referred to as the just noticeable difference, J and D. As they studied this, they found that the just noticeable difference was always a consistent proportion of the original stimulus. In fact, this was so consistent, it's one of the few things in psychology that can be called a law. This happens to be called Weber's law. Unfortunately, not any of my relatives, but anyway. So to illustrate this, let's say, for example, let's say we're moving a large refrigerator up a stairway, and you're at the bottom providing most of the pushing power, and I'm at the top more or less guiding it for the most part. Let's say that I place a piece of paper on top of the refrigerator. Will you notice a difference in the weight of the refrigerator? And you said, well, of course not. Um, okay, why? Well, the paper is so small in reference to the original stimulus, the refrigerator, that you will not notice the difference. Now, what if I put a 200-pound barbell on top of the thing? You're going to say, well, of course you're going to notice then. Why? Because it's very large in reference to our original stimulus. So for an example, they found that when it comes to lighting in a room, you have to change the lighting up or down by 8% before people will notice that the lighting has changed. Or in comparing two weights, the 2% is the smallest difference that people typically will notice a difference between two weights. Or when it comes to pitch, this is really interesting, 1/3 of a percent. So that's a very tiny difference in pitch, easily noticeable to the average person. I thought that's pretty interesting. Yeah, even if you're not a musician, you notice it real quick when somebody's singing a little out of tune, right? So these difference thresholds can we tell a difference between two stimuli. Okay, now signal, let me get this out of the way. Signal detection theory and then goes a little further and looking at the likelihood that we'll detect a particular stimulus, then we need to take into account a number of things, not just the intensity of the stimulus, how much stimulus energy, like what we were talking about before with the absolute threshold, but also whether we detect that may depend upon the amount of background stimulation. So as an example, um, suppose that you're at a concert with very loud music and I call you on your cell phone. Will you be able to hear me speaking on your cell phone? And you say, no, I can't, I wouldn't be able to hear you. Why is that? Is the sound coming out of that cell phone of my voice, is it above the absolute threshold? Well, yes, it is. Well, then why can't you hear me? Oh, because there's too much background. Yes, the background stimulation makes it impossible for us to pick out that stimulus, even if it's above that absolute threshold. So that's an example. Visually, think about this one. Can you detect the color of the traffic light as you approach the intersection? Well, it depends. If you're looking straight into the sun, you may not be able to see it because, again, there's what? Too much background stimulation. Or maybe you're trying to find your friend in a large and crowded football stadium. Again, you may have difficulty picking them out. Why? Too much background stimulation, too many other people there to pick them out readily. So background stimulation. By the way, this is called, in research, it's called noise, whether it's actually music or whether it's something visual. They call that background stimulation noise because it's what? Something that's not part of the signal that we're trying to detect. The third thing would be the current biological and characteristics of the perceiver. So biological factors that play a part would be the condition of your sensory apparatus. Yes, if your ears have been messed up by years of shooting and working with loud machinery, like mine kind of have been, um, yeah, you may have difficulty detecting stimuli that other people can hear, right? Or another biological factor might be your overall state of consciousness. In fact, if you have taken a large amount of depressant drugs like maybe alcohol, yeah, you might not be able to detect that somebody's tapping you on the shoulder, right? So biological characteristics of the person at that moment, as well as psychological characteristics. And here's an example. Suppose that you're walking down the hallway uh, at school and you're on your way to give a little class presentation that you've worked up. And so you're going over that thing in your mind and you've had many good experiences at school, so you're very comfortable walking down that hall, very calm and comfortable, even though you're thinking about your presentation. Are you likely to detect the sound of everyone else's footsteps in the hallway? You say, no, you're not going to notice that because you're calm and because your mind is on something else, selective attention. Now, on the other hand, let's change the scenario. Suppose that you're in a quote, rough neighborhood and it's 3 a.m. in the morning, very dark, no street lights. Are you likely to detect the sound of footsteps nearby now? You say, well, yeah, you sure would be, because why? You're on the alert. And so you're going to now detect things that you wouldn't normally. So your psychological state also plays a part in whether you detect a particular stimulus. All right. Another factor in our awareness of sensation is sensory adaptation. Sensory adaptation is a fading sensitivity to an unchanging stimulus that we are exposed to for some significant length of time. So as we're exposed to that unchanging stimulus, our awareness of it fades. An example of this would be if you wear a watch. Put on the watch at first in the morning and you feel and notice the weight of the watch on your arm. But later on in the day, you find yourself asking people, hey, what time is it? And they say, well, I don't know. Why don't you look at your watch? And you go, oh, yeah, I forgot I had it on there. You don't feel the weight of it anymore. Or maybe you go to a friend's house and you come to the door and you go, "Ooh, man, what's that smell? Oh, I don't know." They got a cat, they haven't cleaned the litter box, and they say, "I don't smell anything." But of course, if you go in there and hang around there long enough, you'll get to be just like them and you won't notice that odor either. Your sensitivity of it has diminished. Or a classic, you go swimming. Water is freezing when you get in, but after a while, you, as we say, get used to it. Sensory adaptation occurs. And then along come your friends and they say, how's the water? And you say, it's just fine. And then you laugh when they get in and freeze, right? So this whole business of sensory adaptation allows us to be less aware of things that are unchanging, where the stimulus is not giving us any new information, so that we can focus our attention on other things that might be more important. Now, this might also make you wonder, well, why don't images disappear when we stare at something? Because according to this, they ought to just fade away, right? Well, researchers found out why that doesn't happen. When they actually tracked the movements of people's eyeballs as they looked at a scene, they thought they were staring directly at the scene, but in fact, their eyeballs were constantly bumping around from object to object within that scene ever so slightly and constantly. And so this kept refreshing the image so that the image was not really unchanging, but always slightly changing. So it never fades. Now, in fact, you can actually force, though, this phenomenon. If you look through a tiny, tiny keyhole or something like that, you will find that if you look long enough, stare through that thing long enough, parts of things will begin to disappear. This may have happened to you if you've looked for a long time through a rifle scope. And you might suddenly get that sort of like a blindness that you can't see through it. You have to take your eye away from the scope for a while, and then before you can look back at it. And then when you do, you can see it again. So you can actually experience that. So this all kind of goes along with what one of our textbook authors, David Myers, has said, which is that we perceive the world not exactly how it is, but as it is useful for us. So it may not be useful for us to be constantly aware of the weight of our body on the chair, but boy, if the chair starts to collapse, then that new information is going to reach our brain, and that's going to alert us that, but all the time that the chair is solid, we don't need to know that it's solid or fine. Okay, so let's go on to then looking a little closer at some of the sensory systems and how they work. We have vision. So the primary stimulus here detected would be light particles or light rays, whatever you want to call them. Either is, you can look at it either way. The wavelength of these gives us then the color or hue, H-U-E, that is perceived, and the amount of light energy that is present then translates to the brightness of that visual stimulus. So here's just a simplified view of how the visual system works. So we have some source of light particles here, which pass through the cornea, the outer covering of the eye, then pass through this pupil, this opening that gets bigger and smaller, Then the particles pass through a lens, which can be, the shape of the lens can be changed in order to focus on things that are closer or further away. Light particles continue through this gel within the eyeball, and eventually they strike the retina, this sheet of tissue at the back of the eyeball that contains our photoreceptors. So within that retina, there's a couple areas that you should be aware of. First of all, there's this fovea, which is sort of the central part of our visual field, and when information falls there, we see it most clearly because we have the greatest concentration of the sharpest receptors there. On the other hand, information like particles that fall on this blind spot, these are not actually registering in our nervous system. Why don't they register? Because there's no photoreceptors here. This is the area where the axons of the optic nerve are leaving the eyeball. So now you may be thinking, well, I don't have a blind spot. I don't see any missing areas in my visual field. Uh, that is true. It takes special conditions for us to actually be aware of that blind spot. If you go to this topic in your textbook, there's an illustration that you can try out, and you'll actually experience an object that disappears when it's a certain distance from your eye, a certain place in your visual field. Maybe you've also experienced this if you drive a car. And as you're driving the car, you look in the rear view mirror, you're about to change lanes, and you don't see anything in that rear view mirror. But as you begin to move over, you hear the horn from a car that is almost right next to you. Why didn't you see it? Well, that car was in your blind spot when you looked in the mirror. And so you didn't see it. All you saw was just roadway, whatever the background. And that's what our brain does. It fills in that missing information there with whatever is most likely to be there. Okay. So that's why we don't perceive that blind spot. And by the way, that's also why they tell you don't just look in your rearview mirror when you change lanes, but also turn your head so that you will get a different view of that scene, that car now not on your blind spot. You'll be able to detect it. Okay, so photoreceptors then are located on that retina. There are two main types. We have what are called the rods. I'll start with them. These are able to function in dim light, but they lack the ability to detect colors. So in dim light, all we see is things in shades of white, black, gray. They also lack good resolution. So we have difficulty making out the details of things in dim light as a result. The rods are concentrated in our peripheral vision around the edges of our visual field. So if you're trying to see something in dim light, say there's a sound in the bushes, some very dark night, how are you most likely to be able to see what's there? Looking directly at it? No, looking at it kind of at an angle from where you actually heard the sound. You're more likely to be able to see it through your peripheral vision as the rods are more prevalent there. Now, there's also the cones. These enable our color vision, and that said, they only can function in brighter light, and so we can't pick out colors well until we have enough light. They also give us the finer details, and again, we are able to then see the finer details when we have enough light, as these cones then can be stimulated. What else was I going to mention? No, that's it. Okay. All right. So here we see then the pathway of visual information from the photoreceptors to the optic nerve. So in the diagram here, we have light particles passing through the retina and striking these rods and cones at the back of the retina. These receptors then send off neural impulses that stimulate bipolar cells. When the bipolar cell has received enough stimulation, it then sends a neural impulse that stimulates these ganglion cells. And when the ganglion cell has received enough stimulation, it then sends a neural impulse down its axon that then travels over the optic nerve. The optic nerve then passing through the thalamus, then relays information to the visual cortex, the back of our brain, the occipital lobe. So that accounts for then how information gets to our brain to begin processing. So Hubel and Wiesel in the 1970s, 1980s discovered specialized neurons that were found in the visual cortex of cats. You might remember the example of the brain lesion created in chapter 2. We showed that. That was actually from Hubel and Wiesel's studies. These feature detectors, these specialized neurons, respond to specific visual features, specific type of stimuli. So some of them will respond to horizontal lines, some to vertical, some to diagonal lines, and so forth. So the way this works is, let's say we have a feature detector that is designed to detect stimulus that is at this diagonal, as you see here by the pointer. When that particular type of stimulus is present in the field, part of our visual field that that feature detector is hooked up to, then it's going to begin producing many, many rapid responses as a result. Now, if we rotate this stimulus to now vertical, you'll notice that the responding slows down. And if we continue to rotate it away from there, eventually the responding stops. So this enables us to begin processing the details of a visual image. Information then that is processed by these feature detectors is then sent on to larger clusters of neuron called supercell clusters that further process it. And finally, information is sent off to specialized association areas of the brain where specific types of objects are identified. In this example, you see the red area here, some facial recognition areas in the frontal cortex of the brain. So various areas of the brain used to identify various types of visual images. So vision also illustrates parallel processing, our brain conducting numerous processes simultaneously. The case in point here is Mrs. M. Now, Mrs. M can see things. She can tell you what color they are. She can tell you what shape they are. That's what they call form. She can tell you whether they're coming closer or going further away. That's depth, okay? But one thing she is unable to process is motion, okay? So notice that this is a separate, each of these is a separate process. The brain is separately conducting these various analyses for color, motion, form, and depth. She lost this particular one. Very strangely, if she saw you approaching, she would see you maybe outside of the room like a snapshot, and then at the door as another snapshot, maybe halfway across the room as a snapshot, sitting down as another snapshot. So that's kind of a weird sort of experience that she's had. Can you imagine trying to pour a glass of milk if you lack that motion perception? Anyways, once again, what's happening is many processes going on. It's all being recombined into that colored moving image that we can identify. So here we see just kind of a recounting this whole thing. I won't go over it right now, but you have a similar diagram in your textbook that you can use for review. Let's move on to the topic of audition, or our sense of hearing. So the stimulus we're detecting now would be sound waves. And we detect two particular qualities of these. We detect the amplitude of the sound wave. Amplitude means the amount of energy, okay? So when there is more sound energy, we detect that as a louder sound. When there's less, as a fainter sound. Amplitude of sounds is measured in dB, or decibels. I think that's actually should be small d, large B. Maybe if you're an audio buff, you can call me up and correct me. So that's the way that we can measure these amplitudes of sound. If we're using an instrument called an oscilloscope that will graph the qualities of sound on a screen, then those sounds with more amplitude produce larger waves on the screen, as you see here. We also then detect the wavelength of that sound. And so this is then the frequency of the sound. How frequently does that sound wave repeat itself over time? So those that have short wavelengths that repeat very frequently, high frequency, are perceived as high-pitched sounds. And those that have a longer wavelength and therefore lower frequency, these then are perceived as low-pitched sounds. In practicing that. We measure these then in cycles per second. How many times does it repeat per second? Or hertz, which is written as Hz. It's the same thing, the number of times it repeats per second. Humans typically are able to pick up somewhere between 20 to 20,000 hertz, or 20,000 cycles per second. Dogs and many other animals can go beyond that range, as a lot of you know. So here's the mechanics of how the sense of hearing works. We have sound waves that enter the auditory canal here, that hole we have in each side of our head. They then strike the eardrum, cause it to vibrate, and this vibration is then transmitted to these tiny bones in our middle ear. The fancy name for these is the ossicles, and they have also fancy names as well. You'll see here the common names are hammer, anvil, and stirrup, because they look like those kinds of things. These are the smallest bones in our body, and given that it is possible to damage them somewhat readily, okay, the vibrations then are passed on by these tiny bones to this structure called the cochlea, C-O-C-H-L-E-A. The cochlea is then filled with fluid and is lined with receptor cells for hearing, referred to as hair cells. Why? Because looking at them in the microscope, they have these tiny hair-like projections. And so when the vibrations disturb that fluid, they disturb those hairs as well, stimulate those hair cells then to produce a neural impulse that travels over this auditory nerve and brings that information to the auditory cortex in your temporal lobe. So that's how we hear in very basic terms. Now, the topic of hearing loss. Hearing loss can occur due to damage to those hair cells, damage to those inner ear structures like those tiny bones we were looking at, or damage to the auditory nerve. Some of this damage can be irreversible, such as damage to that auditory nerve or those hair cells. And so it's a good idea to protect ourselves against hearing loss. Now, what does it take to produce hearing loss? Now, some of this can happen due to infections or something like that, but the most common cause of hearing loss is simply exposure to too much loud sound. So in this diagram here, it's showing the differences between various levels of sound. This is measured again on the decibel scale. Each time you go up 10 points on the decibel scale, you've also multiplied the amount of sound energy by 10 times. So if you do the math, it's not real hard to do, you will find that a rock band at close range is 100 million times more powerful in terms of sound energy, 100 million times more than a normal conversation. And when you look at it that way, it's no wonder that sounds of that level can damage our hearing very rapidly. So what is the thing that we can do to protect against hearing loss? Quite obviously, when we're exposed to sounds, and they found anything actually above 85 decibels for any length of time, we should protect our hearing by using earplugs, earmuffs, or even doubling them up, which is what I do when I go to the shooting range now, so that I can maintain whatever hearing I still have. So that's a good idea to do that. If you can't do that, you can stick your fingers in your ears temporarily, but try to get out of the situation so that you can save your hearing. And I don't know, a lot of people when they're younger, they don't think anything of it. But when you get older and it accumulates, then you realize that, yes, you should have tried to save your hearing. So pass the word on about that. Okay, let's move on to the sense of touch. So the sense of touch is very vital to our development and survival. In newborn babies, being touched and handled actually helps release hormones that are necessary for normal development. Babies that are not picked up and handled may, as they call it, fail to thrive. And in other words, even given good nutrition, they may not be able to utilize that nutrition. They may waste away and even die as a result. So the sense of touch is very important to our very early development. Also, we find that separation uh, also illustrates the importance of touch. When they took baby monkeys and they separated them from their mother with a screen where they could see their mother but not touch her, they became very, very, very disturbed. On the other hand, when they had an opening in the screen where the little monkeys could place their fingers, I guess you'd call them, through that hole in the screen and touch their mother, they found that to be oh so much more comforting. And so that also points out how that sense of touch is so important for us. The sense of touch is important for communicating emotions as well. Think about it. Yeah, you can say I love you all day long, but it doesn't mean as much as a hug or a kiss. So touch is very important for us. And oh, let's not forget that for our survival, yeah, without our sense of touch, you might what? Have your foot in your the campfire all night and not even know it and burn your foot off, right? So sense of touch is extremely important. Here's the basic types of touch sensations. We detect pressure on various parts of our body, as well as warmth and cold and pain. Our sense of touch may be as much a matter of our expectations as it is actual sensory information. And that was illustrated in an experiment that was done called the rubber hand illusion, or became known as that. So researchers had one of these rubber hands, maybe you've seen one of these things, and they would bring people into their lab and have the person put their real hand inside of a box. And then the researcher would touch their real hand and the rubber hand together with these calipers. The person was to always tell the researcher every time that they actually touched then their real hand. Well, after doing the two together a number of times, the researcher surreptitiously adjusted the calipers so it would only touch the rubber hand. When the participant saw the caliper touching the rubber hand now, they reported that, oh yeah, you touched my hand, okay? They actually felt it in their real hand, even though it had not been touched. So this illustrates how expectations can produce sensory information that is matter of expectation. Now, this also shows how our senses interact. We tend to go with what our visual system tells us over and against our other systems as well. So let's spend a little time talking about pain sensation, and we'll kind of bring in a little bit of perception. It's kind of hard to keep them apart here. We're talking about it. This one, I think I like to spend more time because, yeah, everybody probably has pain at some point. It's good to understand it better, as well as many of you will be going into professions where you might deal with people who are experiencing pain. So it's good to understand it well. And I'm going to tell you that probably even 25, 30 years ago, they didn't understand it nearly as well as they do now. About that time, the biopsychosocial model of pain uh, came out or got started. And rather than seeing it simply as a biological phenomenon only, they recognized that psychological and social factors were as influential as the biological ones. And to really understand pain, you had to understand those aspects as well as the biological aspects. So one of the things that came out of this whole study indicated that pain is not equivalent necessarily to mere tissue damage. And in fact, there could be pain without tissue damage, or the pain could be out of proportion to damage to the body. They also then discovered or proposed that there was something going on within the brain that served as sort of a central regulator system. And this analyzed all of the biological pain indicators as well as psychological factors and social factors, and took those all into account to decide, should we feel pain? And if we should feel pain, well, to what extent should we feel that? Okay, so this then was not just a matter of there was something wrong with your body and the pain was in proportion to that, but rather interpreting that, sending it through a bunch of filters. Okay, so first of all, let's look at some of the biological factors. And in this example here, we do indeed, I'm having a great deal of trouble with my cursor here. I'm going all over the place trying to get it, to get this here going. Let's see if that's not better. I'm sorry. Let's see if I can get that. I'm spending a lot of mental energy trying to get the cursor to go where I want it. Now maybe this will be better. Okay. So in this case, we have some tissue damage, pain generator, that has occurred, okay, an injury. So in this case, have you ever noticed you got an injury? Sometimes it hurts worse than others. And you say, well, why is it the injury hasn't really changed, but yet I don't feel it as much now as I did before, and so forth? Well, one of the explanations of this that came up was called the gate control theory, that there was some gating mechanism in our spinal cord that was able to stop the pain messages from being sent on to our brain. When they began to study this, they actually found out that that was a very accurate sort of theory. And they found that there were special neural fibers that conducted pain messages towards our brain and our nervous system that were bundled up with larger fibers that conducted the information from various other stimuli. So conducted the messages of movement, hot or cold, and pressure. When these larger fibers were active, carrying some of those messages, that had the ability to shut down the transmission of pain messages in these smaller fibers. So indeed, that was an actual mechanism. Now, you might actually have had the experience then of utilizing this in real life, okay? How can you activate this gating mechanism intentionally to feel pain less? Well, here's an example. Let's say you've twisted your ankle a bit playing some sport. If it's not very serious, what does the coach say? Yeah, if you want to be a coach, you got to memorize this one. The coach always says, walk it off, right? It's like a classic. Well, you indeed do some walking and you find out, yeah, hey, it doesn't hurt as much as I thought. Yeah, what you've actually done, you've sent stimulation for movement through those larger fibers, shut down those smaller fibers carrying the pain message. You don't feel it so much anymore. Of course, you can do this in other ways. You smack your finger with a hammer, and what's the first thing you do? You go, I curse. Yeah, okay. Well, after you do that, yeah, usually what you'll do is you'll start to you'll start to rub it, you'll start to massage it, right? And so you're using pressure to again activate these larger fibers and shut down that pain gate. We can also do this by imposing heat or cold. So now, of course, you probably don't want to put heat on something that you just recently hurt within the last few hours because it might make it swell more. But after that point, you could put heat on it, and often, yeah, it feels better. Yeah, grandma has that heating pad, that she might use for aches and pains, hot water bottle, or we can use cold as well to do that. The nice thing about cold is if you have heard it recently, it also can reduce the swelling, right? As well as shutting that pain gate. In fact, researchers found that one of the best ways to activate this mechanism was actually alternating heat and cold. Okay, so we can intentionally change our pain threshold doing that. They found out also that part of this whole mechanism is this required the release of endorphins within our nervous system. It turns out that there is some genetic variation in people's ability to do this. Some people are more capable of that than others. So we have some people that are just basically more pain tolerant than others. Okay. So we also then have our brain's interpretation of the central nervous system activity. And so as our brain interprets what else is going on, in fact, our brain can create sensations of pain in absence of tissue damage. This happens, for example, with phantom limb pain. People who have had limbs amputated often will say they feel pain in that limb even though it's not absent. And so the brain is creating this sensation of pain. There is also the phenomenon of sensitization of the nervous system through exposure to pain signals. So if we have experienced an injury somewhere, then as those nerves that are carrying those pain signals are doing this repeatedly, the connections, the synapses within those neural networks are strengthened. So now that neural network is able to carry those pain messages more effectively. And the threshold for activating those neural networks for pain also are more sensitive and can be activated by less and less pain as those neural networks are strengthened. And so that sensitization can occur on a local basis. In other words, between the site of the injury and the spinal cord, or it can also occur, as they say, central within the spinal cord and within the brain, so that now even slight bits of pain, slight tissue damage in an area produces pain out of proportion with the actual tissue damage, or maybe when the thing is completely healed, even mild sensations of stretching and so forth might actually activate that and be perceived as pain. So, yeah, that's something to be aware of as well. We also have numerous psychological influences on the perception of pain. And one involves our attention to that pain or distraction from it. As you see in the picture here, researchers had participants to sit in a tub of ice water. And believe me, that will get painful very quickly. Some participants were simply told to, yeah, tough it out, and just, tolerate it as best as you can. Others were distracted by scenes of pleasant snow scenes and pleasant music and so forth while they sat in the tub of ice water. And here's the differences in how their brain responded. Areas of pain in the subjects who were not distracted were much more active than when those who were distracted, much less activation of those areas registering the pain. So distraction, one of the psychological techniques we can use to reduce sensation of pain. Observational learning also comes into play. We have specialized neurons within our brain called mirror neurons that respond when we see others experiencing something. When we see others in pain, those mirror neurons actually respond to that as if we were feeling the pain. Now, not as much, but to some extent. So, yeah, somebody say it was painful to watch them go through that procedure. Yeah, we kind of experience a bit of that, especially if we empathize with them. That actually influences how these calcium channels in our neurons are actually responding as well and becoming more sensitive in responding to signals related to pain. So as we observe other people experiencing a painful thing, we may find it so. And then emotional learning as well, whether we saw somebody else in pain and felt the emotion as a result of observing them experience pain, or whether we have experienced it before in a similar situation, that fear causes our brain to remember it so that when we're uh, coming into a similar situation again, we're going to have a greater fear of it, and therefore we're going to feel the pain more readily. Expectations as well. If we expect something to feel a certain way, we have a tendency to have something that follows. I'll tell you a little bit about that in a bit. And then we have also the evaluation of what that pain means to us. So a couple examples here of that. One of the things was back in World War One. They had this odd phenomenon they noticed that sometimes soldiers that were injured on the battlefield, they basically felt almost no pain. And it was very odd, especially when that meant that they were going to be removed from the theater of battle. And they eventually figured out that the reason was that this was sort of a relief from all the stress of being on the battlefield. And so the fact that they were injured actually was interpreted by them as being something good. They were going to get to go home instead of being out there on the battlefield. So how we evaluate the meaning of it. Another example might be, have you ever seen this little kids? Maybe they skin up their knee, and a lot of times they just keep running. They don't care, no big deal to them until mom sees it. And mom sees that skin, and go, oh my God, what happened to you? And then what happens? All of a sudden, now the kid is like, ah, and then they're crying, right? And notice that mom told them that, oh, something terrible has happened to you. Now they cry, now they feel the pain. But without that, it really didn't register. Oh, and here's a final example. Maybe you experience an injury, and it means that injury is going to end your athletic career. It's going to hurt all the more when you think about it and you think, ah, I'm going to be ruined for life now. Yeah, that's going to make that pain even more intense. And then simply the levels of stress that a person is under. The more stressed they are, the more anxious they are, they found the more people are likely to register that pain. And that's probably part of that, central regulator theory that we talked about earlier, that the brain is putting all these things in calculating how much pain we should feel and so forth. Now, next, I'm going to try to move this thing here. Okay. We have social influences on pain. So, support versus isolation. When we're in a supportive environment, there's someone there supportive, we don't feel the pain as much. But if we feel isolated, if we're alone, we tend to feel pain more. And, think about this. How many women would really want to give birth alone? No, everyone wants someone supportive to be there with them, in part because, yes, it makes the pain more tolerable. So that's important as well. Then cultural expectations. I'll give you a little bit of a complicated example here. It's not complicated, but I have to give you a little more information on this one. Now, if you get into a car wreck and somebody hits you from behind, what are you going to expect is going to be the result of that? And most people, most Americans say, well, you're probably going to get whiplash. Well, it turns out there's some places in the world that people don't get whiplash in those kind of situations. So what am I talking about? Okay, well, let's go across the ocean to part of the world. In Norway, Northern Europe, Scandinavia, they get whiplash just like we Americans do in these situations. Now, they have insurance that will pay for it, and it's become a diagnosis. There are treatments for it. But right across this little, a few miles of ocean, another country, genetically, people are very similar, but they don't get whiplash. Why not? In Latvia, insurance does not pay to have this treated. Their medical system does not use the diagnosis of whiplash. In fact, people there don't even know what it is. And so they found that, yeah, in Norway, high percentage of people in these situations would get those neck pains after that type of accident. In Latvia, very rare. And the few people that did experience that kind of pain after that sort of accident usually said, it was just a couple of days and it went away. Okay, so what's going on there? Cultural expectations have produced expectation. We're going to have that result, and therefore our brains produce what is expected in our cultural situation, or in this case, the Norwegians and the Latvians. But that kind of applies here in the US because we've taken on that and any number of other sorts of pain syndromes that we have been told are common and so forth. Which kind of leads us also to suggestions made by an authority figure. Okay. And so I was trying to think how to approach this carefully. Okay, so let's say that you've been having, I don't know, some back pain. And so you go to a doctor and they run an MRI and they find some abnormalities there. Okay. Now, if you have experienced back pain under those circumstances, it is likely to persist much longer than if you go to that authority figure and they say, it's probably not a big deal. Tell you what, why don't you just, do some stretching and maybe do some of these exercises here and let's see how it is in a few months. You're much more likely to get over it with that second set of suggestions than if the authority figure suggests that there is something significantly wrong with you. Okay. Now, in fact, even having a test to see if there's something wrong there, like an MRI, increases the likelihood that you'll experience long-term pain in that area than if you don't have that. Now, don't get me wrong. There are situations where you need to have that MRI and so on. But in many situations, it may not be necessary to actually have that test, and you may actually find your pain goes away more readily. This is also kind of consistent um, with a whole thing we call nocebo. Placebo, you know what that is. Placebo, I will please. And so, you're suggesting that something good is going to happen, and we know that's real. Nocebo is just as real, where some authority figure tells you that there's going to be a negative outcome, and indeed that happens, and happens more so than where there's not that suggestion. Okay, well, I could go on a lot further with that, but I'm going to leave it there for that. If we were in classroom, I could talk a little bit more about it. But let's just sum up some of this stuff. So biological influences on pain, the activity of those large and small fibers in the spinal cord, genetic differences in our ability to produce endorphins, and how our brain is interpreting our central nervous system activity. Psychological experiences, our attention to pain, or whether it's distracted on something else. Learning based on experience and our expectations. And then social cultural influences, the presence of others, empathy for others' pain, and cultural expectations all play into our personal experience of pain. All right, on to taste. So taste is one of our chemical senses, and we are detecting chemicals, molecules that are in food that we take into our mouth or anything that we do. We have receptors for 5 types of tastes: sweetness, saltiness, sourness, bitterness, and umami. These seem to have survival functions for our ancestors. So being able to detect that something is sweet might suggest that it is something that could be eaten for energy. Saltiness producing, containing minerals that might be necessary for health. Sourness, maybe the thing is spoiled, not good to eat. Bitterness, potentially poison. And umami, containing some protein substance that might help us build our body back up. Yeah, that's the one that people have never heard of, umami, simply as they refer to as a savory taste, protein-rich foods. So sense of taste, very important. Now, this sense of taste actually does not stand alone. It actually works together with our sense of smell. Another example of sensory interaction. I think I'll come back to that in a minute. So let's talk about olfaction, which is our sense of smell. And you'll notice that this depends upon olfactory receptors in our nasal passages and sinuses, that these send then information over the olfactory nerve, and then that is interpreted in our brain. You might be surprised that humans actually have a fairly well-developed sense of smell, not as good as, say, dogs, but better than you might expect. And I'll give you a couple of examples. Did you know that newborn babies can tell the difference between a diaper that her mother has handled as opposed to only handled by a stranger? The newborn will find the one handled by her mother to be comforting, the one handled by a stranger to not be comforting at all. They can actually tell by the sense of smell. Now, you might think that that ability goes away as you get older and become an adult, but maybe not so. Psychology researchers had student volunteers bring their pets to the psychology lab. That must have been an interesting experience. They then blindfolded each of the students, made sure they couldn't see, and then had them sniff each of the pets and to try to, without touching and seeing them, try to guess which pet was actually theirs. they found that over 80% of them were able to identify their own pet just by sniffing. Although they weren't very confident of it, they were able to do it for the most part. So again, our sense of smell may be much more capable than we give ourselves credit. Dog. I have to let my dog in. Okay. Now, have you ever noticed that various scents often capable of activating memories and strong emotions? Yeah, you know, you smell a certain cologne or perfume, and immediately someone who you haven't seen for years comes to mind. Or in my case, if I smell the scent of some rose scented soap, I remember junior high locker room because they had some rose scented soap in there. It comes to mind right away. So you might wonder, why is it that these things can activate our memories and emotions so readily? Part of it is that areas that process taste and smell are very near the emotional centers and the, sorry, I'm distracted with the dogs here, emotional centers and memory centers of the brain. And so that will pull up those emotions. And okay. Next, we go to kinesthesia. This sense, maybe you've not heard of before. Kinesthetic sense is another way to say it, kinesthetic. This involves receptors in our joints, ligaments, muscles that then register movement and position of body parts. So the kinesthetic sense registers movement and how our body parts are positioned. So it tells us, is my arm bent? Is it straight? You know, is my arm above my head? Is it out to the side? And so on, how those body parts are positioned. Now, you might not think that's a big deal, but there's actually been people who've lost this ability, and they literally have to look and see how their legs are positioned, their arms, and so forth. Then we have the vestibular sense. This might be one you haven't heard of before, unless we say, oh, it's your sense of balance. And then everybody goes, oh, I get it. Yeah. And so what this actually does is this actually keeps track of how our body is oriented versus the ground. You know, are we in the horizontal position and kind of laying down? Are we in the vertical position and standing up, or somewhere in between? And are we maybe tipping too far over where we're going to have to correct, or we're going to fall down and all that sort of thing? So give us from our vestibular sense. The way that this one works is that we have these tiny tubules above the inner ear area, semicircular canals, that are very similar to the cochlea in that these are filled with fluid also, and also lined with hair cells. And whenever we move our head around, then that disturbs the fluid in there, therefore these hair cells, and that indicates to us that we've moved. These semicircular canals then are also the source of, we have motion sickness. Okay, so maybe you played that game where you put your forehead on a baseball bat and put it on the ground, and then you spin around that thing a few times, and then you try to walk a straight line and you can't do it. Everything seems to be spinning around even though you're now not spinning around. Why do you have that happen? Well, because that fluid in these semicircular canals is still sloshing around, and so you feel as if you're moving. Gives you that sensation when your eyes are telling you you're not. And in some cases, this can even lead to motion sickness. So there you go. A lot about sensation, and the next video will pick up perception and talk about how that works hand in hand with sensation. So that was a lot. Let's call it quits and hope you're having a great day. Bye-bye.